project, and yes, and he's a member of IPK, which is a well-known institute in Berlin, and they have done a lot of contribution to our project, and among them, Robert will talk about modular ontology design for semantic data integration. It is co-authored also by Mr. Geitler and Dr. Heike. The floor is yours.
First of all, thank you for your patience. We should already be in the coffee break, so feel free if you prefer a coffee, but I'd be happy to have you staying here. All right. So the presentation is about modular ontology design. I'll get to what that is in more detail. I will not introduce the project again, you've heard about it. So this is the main flow of the agenda, presented as a process model. First, I planned to present to you challenges in engineering associated with heterogeneous distributed data. I think I will jump over that point because it's the same song all over again, and that is, yes, we have a lot of information in engineering. It's distributed over many different systems. It's hard to get it out of the systems, especially this data is usually not interconnected, and there are quite a lot of engineering activities where you need a lot of information that you cannot retrieve only from one system. So how to get it? It requires a lot of time, and so it's the typical heterogeneous data problem that we're addressing. And in our project, this is an old problem, it's not new at all. There have been a lot of approaches to integrating data from distributed systems. And in our approach, we are using ontologies as data integration models, that is, models that we use to link distributed data. And in the second chapter, I will try to explain to you why we use ontologies. What was our motivation to use ontologies instead of old school relational database models? I'm not saying they're bad at all. I'm just trying to tell you the advantages of it. Then I will get into detail, and that is how to design these data integration models as ontologies in order to make them flexible for later adaptation. And in the third step, I would like to show the actual architecture of ontologies that we designed in the project. And if I still have the time, I will present you some examples and how our model can provide the necessary information to make these processes a little bit easier in the future. Okay, as I said, I will run through this. You can ignore it. I just want to save some time. So, why do we use ontologies? First of all, ontologies are vocabularies, like a dictionary, and they are usually written in human language. So if you look into a database, often you will find cryptical names for tables that no normal user will ever understand. Here, from the beginning on, we create data models that are easy to read, also for non-experts. I will not go into that into much detail. The next examples are much more interesting. We are using ontologies because that data format allows us to use some free-to-use tools on the market. On the one hand side, graph exploration tools that will help users to find information in different ways than before. I'll present to you that in the next slides. And we can apply reasoning. So I'll first get into the data exploration tool. And that is that. For example, I tried a tool, there are free tools. I said, yesterday I just opened this tool called GFacet. You can connect it, it's a web-based tool, you can connect it to any kind of ontology-based data store. Here I connected it to DBpedia. It's a copy of Wikipedia, but semantically interconnected, and it uses this kind of ontology data format. So what I did is, the typical scenario for using such a tool would be, I start with one item, like I did with the Acropolis of things, and I want to explore what other information is linked to it. Because typically, the user, for example, using a PDM system, if he wants to search for something, well, he needs to know the ID, or he should know exactly what he's searching for. But often, you will know exactly what you're searching for. You might just be interested in, I'm changing some item. Who else is affected by that change, for example? You can't really tell, please give me all manufacturing processes that are related to that item. There might be other things connected to it, but in order to find out, you have to ask specifically. And here you can basically open the Acropolis of Athens and see what's connected to it. So I found that it has an architect who was Callicrates, I think. It was made out of marble. It's in Greece, and Greek capital is Athens, for example. So you can start exploring this graph of information, and it will help you, or can help you discover connections that you weren't aware of before, that you would have never found if you had only queried specific queries. Now, the next example is a little bit a different approach. If you want to know how two items or more items are linked together. So for example, I would say, I have this requirement and I have this test. How are they related to each other? Maybe the test verifies exactly that requirement. Maybe the test works on some product structure element that is over 6 knots and nodes in the graph connected to that thing. So here what I try to do is I enter, it's another tool, I enter two items and I want to find out the relations between them. So I entered Pythagoras and mathematics. And it found quite a lot of connections between the two, and you can filter them. So here I saw only the connections that are directly existing between them. For example, Pythagoras, his main interest was mathematics. Now I changed the filter and I could see that there are indirect connections between Pythagoras and mathematics. For example, Euclid or Kepler were, I don't know in which direction they were influenced. Kepler was later. So Kepler was influenced by Pythagoras, and Kepler also focused on mathematics. So you can find indirect connections between them. And yeah, this is when you go through 3 different levels of connections. But this can be quite interesting to explore how items are related to each other. To sum it up, information is more accessible, or in a different way accessible. Users do not need to learn query languages, which is quite nice because it may take quite some time in a PDM system to learn how to query data, for example. And users can find information without having to know what they are searching for exactly. You can just start exploring. I mean, you can also spend a lot of time like that, but sometimes it will help you find information that you would have not found otherwise. Now let's get to reasoning algorithms. Imagine you have a requirements management system and a product data management system. You want to link data. Basically, you have doors and a team center, for example. You want to link requirements and doors to product structure elements in team center. You need some kind of data integration model. So here is a very, very simplified model. You would say, okay, in that model, we just have the concepts requirement and product element. Requirements can be hierarchically structured in a tree. Product elements can also be structured hierarchically. It's very simplified, I know. And requirements can refer to product elements. And we have this linking model, and we have mappings between the proprietary systems and this model so we can link data. So this is the kind of thing you would like to have. Now, if we do this with ontologies, we can add logical rules to this linking model. For example, if a requirement has a sub-requirement, B, and that and A applies to a product structure element C, then B also applies to C. What does it mean? Well, before getting into there, I will give you another example because this can take quite some time to explain. Imagine, I'll go one step back. Imagine you have a requirement that is a weight constraint. You link it to a motor, and you say motor shall not exceed this weight. And then you have a user who's responsible for some subcomponent of that motor, and he would like to find out all requirements related to that component he's responsible for. Now he would query the system, and the system would tell him nothing. There's no requirement for you. Why? Because the link between the weight thing and the motor was explicitly specified, but not between the weight and that subcomponent. For us, it's clear that it must also apply to that subcomponent somehow. That's clear, but not to the computer. It's not that intelligent, so you have to add that intelligence by specifying rules. And this is what we do here. So basically what would happen later on, I will go through that quickly only. Imagine you have data already, you have specified requirements, you have product structure elements, you have links between them, and you can apply a reasoning algorithm, and it will derive more links. Like for example, that this weight constraint would also apply to the subcomponent. Obviously, you would find out some weight constraint that is a little bit more than you're allowed to use, but at least you know that there is a constraint. Good. So what does it do? Basically, you can teach simple logics to the computer by specifying them in the data model. Implicit information can be discovered. Implicit information that would have been, it's clear for us that there is a connection, but this is also why sometimes you have to search a lot, because you have to think, what does the computer not know? So I have to search exactly for that. And data linking can be semi-automated. Right. Next step. How to design such ontologies in order to make them flexible. Now, I have only a few time to go through that. Let's revisit that example. Simple integration ontology. Now, to generalize it, basically what we have here, we have two data formats, the one from the requirements management system, the one from the product data management system, and we have an ontology and a mapping between. This is the general view on it. We did that, by the way, for Team Center and goals. We did such a thing, and yeah, we used requirements interchange format and PLM, XML, created mappings to an ontology. Through this way, we exported data and created links between them. Now, this is nice, it works, but there's a little problem with it. If you decide now that, wait, I also would like to link tests to my requirements, and you have third system, say an Excel sheet where you have a list of tests. You want to link a third system to that ontology, you obviously have to change that ontology. Now, this means every time you want to insert a new system into your architecture and link it, you have to modify that central thing. It will grow, it will become more complex, harder to manage. So ideally, you would take a little bit a different architecture approach. Instead of having only one ontology, you would create one ontology corresponding to that one external data format, and another ontology for the other, and integrate them here. Why? If you add another third system here, you can create an ontology for it without interfering with those, and add the links here. This is just a more flexible approach. In our applied to the example, that would be first, you have ontology, product ontology, and requirements ontology. It's very simplified. Obviously, there would be more concepts in it to extract data, but let's just say for the beginning, we have these two different ontologies. Now the question is how to link them. And we had a look at how you can link ontologies to each other, and basically identified three different patterns how you can create such links. First one is that. What we've seen before, actually. You have these two ontologies, and another one that imports them, and by importing it, it will directly import these two concepts. And now in that ontology, you specify the link. So since you cannot do it directly here in between them, you have to specify that ontology. That's the usual way that you would find an ontology integration, the classical approach. But there's another one as well. By the way, this is usually done when, for example, you make a research on the internet on ontologies that exist. You use them for your project. You don't want to change them at all. You want to specify links between them. This is the approach you should take. Now, the other approach is a little bit different. You still have your two different ontologies, but instead of having one that inherits from them, they both inherit from another. Now, let's go through that example. Imagine you have some high-level ontology that says, basically you can link systems to requirements, but it doesn't say anything more about them. You can specify more detailed ontologies in which you add details, like this. You would say, okay, I want to be able to link systems to requirements, but in that upper ontology, I don't need to know all the details about a requirement, all the details about the product structure. I just don't need it at this detail level, but I can add more detail at a lower level. This is a useful approach when you develop multiple ontologies yourself, and when you already know from the beginning on that you're planning to integrate them. This can be very useful. And then there's a third approach, and that's to combine both, called the hybrid integration, and that would look like this. We've seen it before, high-level ontology, just the high-level concepts. On a lower level, you have additional concepts for requirements management view, for a product management view. But here you can only link systems to requirements. You cannot link parameters of a system or to attributes of a requirement. So if you want to link them at a more detailed level, you can create another ontology down here and link them at a detailed level. So the charm about this approach is that if you have multiple ontologies and you want to link them at different detail levels, this can be very useful. And this is what we've done in our project. So my time is over. I'll quickly show you our ontology architecture that we have. We have some kind of generic ontology in which we have high-level concepts like you have systems, requirements, tests, but we don't say what kind of attributes a test can have or what kind of expressions you could specify in a requirement. All this is specified in the more detailed ontologies. We have one for project management, which specifies concepts like phases, milestones, responsibilities. We have process ontology with sub-processes, activities, tasks, events, decisions, requirements management, in which you can also specify specific relations between requirements, like a requirement has been derived from another, or is a copy of it, etc. So we have more detailed ontologies on this level, and we link them down here. So high-level concepts are up here, detailed concepts are down here. And now, please let me know how much time I have left.
I think
Quite a lot.
I let you.
Quickly go
You
through.
can have an extra 5 minutes.
In the beginning, in the very first chapter, I introduced, you haven't seen it, I introduced 4 different use cases, engineering use cases in which you require a lot of distributed information. And I'll quickly go through some examples and show you how basically our data model can provide the necessary information for those use cases. You still have to build systems that will retrieve the data from this data model, from the data storage, but I just want to show you that we cover different things. By the way, I have already mentioned it. We created mappings to existing data formats, so you can export data from an MS project, for example, file, and then you have it in ontology format, or requirements in a record file, and then you have them, can use them in our project. Same for step 233 and PLM XML. Okay, here's an example. Here were the 4 examples. Intelligent data reuse is something that has been mentioned before and that has been shown also in a specific example. You might want to reuse requirements and product structures from prior projects. I won't go into that into too much detail. I will just show you one example now because I don't have a lot of time. That's engineering change management. And in engineering change management, this is usually companies use it when you notice during development that there's some item that doesn't work the way it has been specified. You would like to change it, but it has already been released in the specification, so you cannot just simply change it. You have to formally ask for it and say, I would like to change this item, and then the experts will try to analyze how this change would affect the schedule, other product structure elements, testing, etc. So all this has to be found out. And this is a change management example. Obviously, changes can affect many different areas on your project. So it could affect the project plan, which is usually stored in some kind of project management system, like MS Project. It could affect requirements. Since you change something and somehow the specification is affected, it could affect other product structure elements that are affected. If I change the weight of one component, then somehow the others usually have to save weight. And yeah, in the next steps you will see. So how can it help our data model? First of all, you could use the iProd workflow management component to formalize your process and let it guide you through the formal process so you don't omit any important step. Second thing you could do is you could identify how changes could affect the product schedule because information is interlinked between the different models. You could identify how changing components affect other components, and you could identify how changing requirements affect product structure elements, because usually these are different models. Here we have the link. Finally, you could persist your decisions and the reasons why you have accepted or rejected a change request using design rationale vocabulary persisted in our system. So next time you have a similar change request, you can quickly go see why it has been rejected or accepted in the past. And finally, you can optimize your schedule after changes. I I have similar examples for the other use cases, but I think I'll stop here, and thank you for your attention.